Welcome to a learning video about linear programming in the course of Operations Management. Every company comes across target-based situations where they try to optimize in order to obtain the best possible solutions. Can you think of any? Say, for example, a company is trying to minimize shipping costs by developing a shipping plan or reducing production costs by making optimal production schedules. One could also be faced with identifying the optimal mix of manufactured products in a factory. When confronted with such situations, linear programming can be a useful tool to solve these optimization problems. But what is linear programming exactly? A linear programming model is a mathematical model in which a linear function is maximized or minimized when subjected to different types of constraints. All these linear programming models have certain characteristics in common. We will assess them into two different groups, those being components and assumptions. You will want to know these characteristics because they will help you recognize problems which can be solved with linear programming. Let's have a look at the components. Linear programming models require that a specific objective be identified. This can, for example, be the maximization of profits or minimization of production costs. Furthermore, one needs decision variables. This means that one can make decisions in terms of amounts of inputs or outputs. For example, in order to minimize the total costs, one has to select a combination of inputs, while someone who wants to maximize revenues has to choose a combination of outputs. Linear programming models include constraints which narrow down the alternatives available to the decision maker. In other words, these constraints are restrictions which limit the degree to which one can pursue its goals. For example, when you are trying to decide how many units of each product should be produced, you are limited by the available machinery. There are three different types of constraints: less than or equal to, greater than or equal to, and equal to. A linear programming model can have one or more constraints. The limitations of a certain problem determine the set of all possible combinations of decision variables. This is called the feasible solution space. The objective of linear programming algorithms is to search the feasible solution space for optimal combination of decision variables in terms of the objective function. As we have seen, a linear programming model consists of a mathematical statement of the objective and of each constraint. These statements contain symbols, so-called parameters, that represent the decision variables and numeric values. Now let's have a look at the assumptions that must be met in order to use a linear programming model successfully. The assumption of certainty means that the numbers in the objective function as well as the constraints are known and do not change for the chosen time period. The second assumption we make is that the impact of decision variables is proportional to the constraints and the objective function. The third assumption is additivity, which basically means that the total activities must be the same as the sum of the individual activities. The divisibility assumption tells us that the solutions don't have to be whole numbers.
This is John. John works out a lot. He wants to get in perfect shape for his summer holiday trip to Mykonos. To maximize his muscle growth, John needs a lot of protein. Therefore, he eats one of his preferred meals for breakfast, either scrambled eggs or pancakes. At the beginning of the month, John buys 3 boxes of eggs and 3 bottles of milk, so 30 eggs and 3 liters of milk in total. In order to save money, John wants to cook as many meals as possible with these ingredients. But which combination of scrambled eggs and pancakes is the most efficient one? John recalls from one of his courses at university that he could apply linear programming, for example, a graphic solution. John has a maximization problem with the following function: the number of portions of scrambled eggs times 25 grams of protein, since one portion contains 25 grams of protein, plus the number of portions of pancakes, again times 25 grams of protein. This is equal to Z, or in other words, 25x plus 25y equals Z. To solve this equation, First of all, we need the recipe for each meal and the overall quantity of ingredients. John has 3 liters of milk and 30 eggs. The scrambled eggs are made of 3 eggs and 75 milliliters of milk. The pancakes of 2 eggs and 300 milliliters of milk. Now we have to identify the maximum amount of portions that can be made out of the ingredients. Therefore, we first have to consider 2 constraints. The first constraint for eggs, 3 times the number of portions of scrambled eggs plus 2 times the number of portions of pancakes is less or equal to 30 eggs. And the second constraint for milk, 75 milliliters of milk times the number of portions of scrambled eggs plus 300 milliliters of milk times the number of portions of pancakes is less or equal to 3000 milliliters of milk. By solving the formulas of the constraints for x, y would also be possible. We get the following for the first constraint. X equals 10 minus 0.67y, and for the second, x equals 40 minus 4y. Thanks to these formulas, we can now determine the permissible range. Graphically, the formulas look like this. By connecting the 2 graphs of the constraints, we can now display the possible output like this. In the graphic solution, you can see that the maximum can be achieved where the constraints meet. Now you can see that the maximum amount of portions and therefore of protein can be achieved by cooking 4 portions of scrambled eggs and 9 portions of pancakes. This results in 13 portions with a total protein content of 325 grams.
Now, in the second example, we will show you how linear programming can be used with multiple factors. Now, he not only wants to maximize the output of protein regarding 2 dishes, but also have a balanced nutrition with minimum cost. Therefore, we will introduce new constraints. We will now analyze 6 different meals regarding their price and ingredients to find the ideal solution. We will now analyze the ingredients of pancakes, scrambled eggs, blueberries, a green smoothie, oatmeal, and a muffin.
Now that John has collected all his data, he has created an Excel sheet. Here, we can see all the different food options and their nutritional values like calories, protein, sugar, and so on, as well as the price for 100 grams of each option. John has done his research on how much nutrients he needs each day for the perfect muffin growth. He split those requirements for the different meals of the day. Here, we see what he set as a minimum and a maximum for the breakfast so he can reach his daily goal of nutrients. Because of that, he uses the smaller or equal signs. In this case, he wants to consume a minimum of 600 calories and a maximum of 1000 calories. Because he's on a budget, he also wants to minimize costs, so his main constraint is the overall price of the breakfast. The price of the breakfast is calculated by multiplying the price with the portion sizes. We can see the formula here. The formula for the amount of nutrients can be seen here. We multiply the portion size with the required nutrients. Now, to solve this problem, John uses the Excel solver, which can be found on the data in the right-hand corner. Here, John first needs to set an objective. In his case, that is to minimize the costs, so he selects this cell and clicks on minimum. He allows the Excel solver to solve his problem by changing the following cells, C14 till H14. Now he goes on with the constraints, so the minimum and the maximum of the nutrients. He goes on to select the reference cells. Then he chooses the smaller or equal sign and selects the constraint, in this case the maximum. He does the same thing but with the bigger or equal sign for the minimum. The penultimate step is not to allow negative values, so he clicks here. Finally, he selects Simplex Linear Programming and clicks Solve. At last, John has found the optimal solution for his nutritional requirements, at minimum cost. To be precise, at a price of 3 Swiss francs and 45 Rappen. To meet his goal, he needs to eat 130 grams of pancakes, 90 grams of scrambled eggs, a bit of smoothie, and 130 grams of oatmeal. In these cells, we see how his requirements are met. Now, John knows exactly what to eat to enjoy a balanced and healthy nutrition. And all thanks to linear programming.
But caution. There are also cases where there is no possible solution or an infinite number of possible solutions. Therefore, I'm now going to present you 4 special cases. First, there are redundant constraints. Redundant constraints are constraints that can be omitted from the linear constraint system without changing the feasible region. Implicit equalities are constraints with inequalities that can be replaced by other constraints without changing the feasible region. Therefore, the constraint does not have an impact and the problem has no solution. Then there's infeasibility. If there is no solution that satisfies all the constraints, for example, no feasible solution can be constructed, then linear programming is not feasible. This could be due to an error in specifying some constraints in a model or some wrong numbers in the data. The third case, I will present you are alternate optimal solutions. An alternate optimal solution is also called an alternate optimal, which is when a linear programming problem has more than one optimal solution. In this case, it is not possible to determine one specific solution. In the last case, unbounded solutions. An unbounded solution to a linear programming problem is a situation where the objective function is infinite. A linear programming problem is said to have an infinite number of solutions if its result can be made infinitely large without violating the constraints of the problem.